Hello, this is Arkasha from MCAT Simplified. Today we're going to be discussing chemical buffer systems. So these are basically systems, usually solutions, that are able to resist changes to their pH within a specific range of pH values. And these are usually going to be composed of some sort of weak acid with its conjugate base. So for example, you can have acetic acid here with its conjugate base in its self form sodium acetate, okay? Alternatively, you could also have ammonium chloride, so this would actually be the acid form, with its conjugate base ammonia, okay? The idea of this is that because you have both some of this base and some of this acid, they're both weak, but if you add in some sort of acid or base, okay, the general rule of thumb is that when you add in a strong acid, it's going to react with the next strongest base that's available, okay, or vice versa. If you add in a base, it's going to react with the strongest available acid. So the idea is that if you imagine like pure water and you add in a strong acid like hydrochloric acid, well, normally what's going to happen is that hydrochloric acid will completely dissociate reacting with water, basically producing pure hydronium or hydrogen ions, right? So the pH decrease is going to be very drastic. But if you have a weak base available in that solution and you add in the hydrochloric acid, instead what will happen is that the hydrochloric acid will react with the strongest base available, which will happen to be that weak base, because the weak base in these buffer solutions is going to be a stronger base than water is. So that acid is going to react with that weak base, and instead of producing just pure hydronium or protons, it's going to produce the conjugate acid of the base it reacts with, which is going to be another weak acid. And that weak acid will then react with water and dissociate somewhat, but remember that weak acids don't really like to react too much, right? Their Kas, or the equilibrium constants of their dissociation reactions, are very small, suggesting that most of the acid does not react. And so the pH change from that entire process will be only minimal, okay, compared to the drastic pH change if you just added the strong acid to pure water. And that's the idea, right? The system is able to resist drastic pH changes by quote unquote buffering any other acid or base that's added, right? So again, to reiterate, if you added acid, like a strong acid, this will react with the strongest available base, which is the conjugate base, like again, sodium acetate, or maybe this ammonia, if it was that one, right? And that will form the weak conjugate acid of that base. And then that weak conjugate acid is going to react with water, but it will only react slightly because, again, it's a weak acid. So you're only going to decrease the pH a little bit, okay? Conversely, if the base is added like sodium hydroxide, then that's going to react with the strongest acid, which is going to be, whatever the conjugate acid is, like acetic acid or ammonium. And what's going to happen is instead of just that strong base added to water, like dissociating, producing a lot of hydroxide, instead of that, it's going to react with this weak acid, and that will form the weak conjugate base. And then that weak conjugate base will react with water, but again, it will only react weakly. So you're only going to produce a little bit of hydroxide, relatively speaking, and the pH increase is only going to be slight, much more minimal than if you had just added the strong base to the solution of just pure water. All right. Now, another important idea is that it is the pKa of the weak acid of the conjugate acid-base pair that determines the pH range of the buffer. Remember that these buffers are only good at certain ranges of pH, and it so happens that the optimal buffer range for any buffer is really plus or minus 1 around that pKa value. So if a pKa value is, say, 5, then the buffer is only going to be good between pH values of 4 to 6. Okay, minus 1 and plus 1. Really, if you start to exceed those pH values, the buffering effectiveness will decrease significantly. Like it's not going to be able to buffer outside of that pH range. And the buffer capacity is determined by the concentrations of the buffer components. So really just the concentrations of the conjugate acid-base pair. And of course, the higher those concentrations are, the more neutralization of any acid or base that you add can happen. So you can neutralize more acid or base that you add to that buffer system if you have higher concentrations of the conjugate acid-base pair forming the buffer. Okay, so now to illustrate some of these concepts, let's look at an example. So imagine we have acetic acid and sodium acetate, the conjugate base. The pKa value for acetic acid is around 4.7. It's a weak acid. So what happens, right, if we have a solution of some amount of acetic acid, some amount of sodium acetate, so the conjugate base, and we add a strong base, sodium hydroxide, right? What's going to happen? Well, think about this, right? So in pure water, we're going to react, in pure water, if we just added the sodium hydroxide, it would react directly with the water. It's a strong base, and it would completely dissociate to form a bunch of hydroxide. It would actually dissociate to form the same concentration of hydroxide as you started with concentration of sodium hydroxide. So all of it would convert into hydroxide, okay? And so the pOH of this would be negative log of the sodium hydroxide concentration, recall, because it's a strong base. And so the pH would be 14. We're assuming this is proceeding at 25 degrees Celsius minus the pOH, right? And the pOH would be whatever we got from this value. It would depend on how much sodium hydroxide we actually added. But then if we had a buffer solution of some sort where we had some amount of acetic acid and some amount of sodium acetate, what would happen is if you added the sodium hydroxide to that, the sodium hydroxide would react with the strongest acid available, which would no longer be water, but would be instead acetic acid. And it would be converted into acetate, the weak conjugate base. And then that weak conjugate base would be the one that reacts with water. And remember, because the Kb, the equilibrium constant for that reaction, is pretty small, it's very small, that reaction will not really occur in large amounts. So you're not going to be producing a lot of hydroxide from that reaction. And consequentially, the pH increase, the amount of hydroxide that you overall add to the solution from this whole process is going to be minimized, okay? Because instead of the sodium hydroxide reacting with water directly, it is first reacts with this acid, which produces a weak base, and then it's the weak base that reacts with the water. And it reacts much less strongly, so less hydroxide is produced overall. Now, this can be illustrated if we look at in like a pH curve form, if we look at the titration of a solution of a known volume and concentration of acetic acid. So we start with some amount of acetic acid. There's no initial sodium acetate present, but we just have some acetic acid. It's like in a flask, in an aqueous solution. And then we're going to be adding a volume of titrant, okay? And the titrant here, we're going to say, is going to be sodium hydroxide, right? So we're adding sodium hydroxide. So we're starting with a weak acid and we're adding a strong base in this case, right? And when we start at the beginning, you know, the pH is going to be, it's going to be low. It's not really going to be like this. It's going to be something maybe down here, right? Because again, if you just have a solution of acid, of weak acid, it will react, right? It won't strongly react, but you will have a decrease in pH, okay? But then when you start adding the sodium hydroxide, it's going to start reacting with this acid, and it's going to be producing some conjugate base, right? Some acetate. And so the pH is going to be increasing, but it's not going to be increasing really drastically initially, right? And then it's going to get to this range here where after you continue adding sodium hydroxide, the pH really barely changes. And this is going to be the buffer region, the buffer zone. And remember that these buffer regions, basically, the range of the buffers, they're going to be within 1 unit of the pKa. And remember, the pKa for acetic acid is around 4.7. So you're going to start seeing this region here on this graph between like a pH of 3.7 and a pH of 5.7. All right. And notice here that as we're adding more and more of the sodium hydroxide, this pH is not appreciably changing. And then we have these two interesting points, okay? So point A is something called the half equivalence point, which is where the concentration of weak acid that's present, right, is equal to the concentration of its conjugate base. So their concentrations are equal at the half equivalence point. And it so happens that if you calculate the pH, if you figure out what the pH is at that half equivalence point, it's actually going to be equal to the pKa, right? And we'll see that in a little bit mathematically. And then point B is where all of a sudden, right, this curve starts to shoot up, okay? The pH starts to change dramatically with only small volumes of titrant, or in this case, sodium hydroxide added. And this is called the equivalence point, B. And the equivalence point is when the concentration of the titrant is equal to the starting concentration of the acid or the base. So in this case, we're dealing with an acid, it's acetic acid, and the titrant is sodium hydroxide. So in this case, at B, the concentration of sodium hydroxide we've added is equal to the total the total initial concentration of acetic acid. And this makes sense because at this point, the sodium hydroxide has effectively reacted with all the acetic acid. So all the acetic acid at that point has turned into acetate, all right? And if you add any more sodium hydroxide beyond that, it will just react with water. And then, of course, we know that that's just going to be producing straight hydroxide ions, and the pH is going to go up really fast. Now, of course, it's not just going to shoot up forever, but it's going to go like something like this. It's going to get to a high pH really quickly, all right? So that's the equivalence point. And these 2 points are really important to know and understand their significance. All right. Now, if we wanted, though, to calculate, given concentrations, if we knew the concentration of the conjugate acid and the conjugate base, and we wanted to figure out, if we wanted to figure out the pH of the buffer solution within this range, right? So we know, we know like the conjugate acid concentration, the conjugate base concentration at a certain point here, but we want to figure out exactly what the pH is. We can use what's called the Henderson-Hasselbalch equation. Now this actually has a mistake. It should be plus, okay? But the general idea here, right, is that pH, the pH of the buffer solution is equal to the pKa of the weak acid plus the log of the conjugate base concentration, A minus, divided by the conjugate acid concentration. So the acid goes at the bottom. All right. So notice that if we say that the quotient, right, of the conjugate base concentration over the conjugate acid concentration, if this whole fraction here is equal to 1, the log of 1 is actually 0. Okay. So then at that point, pH is equal to pKa. And this quotient here would be equal to 1 when their concentrations are equal. And remember that happens at the half equivalence point. All right, so this equation will show us why at the half equivalence point, when the weak acid is equal to the weak base, the pH is equal to the pKa. All right, and this is the Henderson-Hasselbalch equation. This equation is only good for pHs within the buffer range, okay, plus and minus 1 around the pKa. And typically speaking, right, what you can do is if you're able to measure the pH, right, using like pH meters and whatnot, and you can use this equation knowing perhaps the concentration or one or the other, the concentration of the conjugate, okay? Or if you knew the concentrations of those, you could calculate the pH at a certain ratio of these concentration, like given a concentration of A minus and a concentration of HA, given that ratio, what is the pH if you know the pKa of the conjugate acid? Okay, and this is a really important equation to know that comes up very frequently on the MCAT. So also notice that if this quotient here, if it's less than 1, right? If it's less than 1, so that means that relatively there is more HA, more conjugate acid than conjugate base. This whole thing would be less than 1. It would be a fraction. So the log of that, of something that's less than 1, is going to be negative. So it's going to be pK minus something, which means the pH is going to be less than the pKa. All right, which makes sense because there's more acid than base in that situation. So it's going to be somewhere in this area. But then if this quotient is over 1, if it's greater than 1, so A minus there's more conjugate base and conjugate acid, then the log of that is positive. So you're adding something positive to the pKa. So the pH is greater than the pKa. So it's going to be somewhere here. Okay. But remember, this equation is only accurate within the buffer range primarily. And that's our video on buffer systems. Check out our website at mcatsimplified.com.